Today we're going to be doing review number 3 for Math 1325. We had 7 different sections going, so we're going to go back to section 5.1. There were 4 sections in chapter 5, 5.1, 5.2, 5.3, 5.4, and then we did 3 sections in chapter 6, 6.1, 6.4, and 6.5. That's what this test covers. So let's go back to 5.1. Find the open intervals where the function graph below is increasing and decreasing. This first idea is the algebra side of this, where you're not really using calculus yet, but if you travel on this blue graph left or right and retrace it with a pencil or a mouse in this case, when is your hand or pencil moving upward and downward and back upward again? So the graph is increasing and it's moving up all the way till I reach that high point right there. And that's an x value of -1. So, and this would continue forever this way. And again, you don't want to go right to left where some people look at this and say, oh, it's going down if I go this way, but it's always about left to right. So if you started out at -infinity, you would be coming up all the way till you got to this point. So the graph is increasing from -infinity until you get to -1. Now, increasing and decreasing, they always have parentheses in the answers, never brackets, because you can't be increasing or decreasing at a single spot. You have to be moving to do that. So until I get to -1, it's increasing, then it's kind of flat for that one moment in time, and then it decreases after that. So again, right at -1, it's going to pick up its decreasing portion right where the increasing stopped. And from -1 until the next change of direction, that's when it's going to be decreasing. So now it's like a roller coaster. Now you're going down until you get here at the bottom, and then it goes up forever after that. So this is a +1 x value. When that occurs, an increase and decreasing is always about the x values only. And then it has a second increasing portion from x equals 1 until infinity. So then whenever there's a second one, you either they sometimes do a union symbol, but I guess they don't have that here. So we just put a comma and do another one from 1 to infinity. And again, these reviews, they're like practice quizzes or tests just to see how ready for the test you are. So we don't get any of the help at the bottom. We don't have ability to check each answer until the end. So I'm going to move forward to the next question. At the end, we'll find out if that's correct. So that one was the algebra side of it. Now we're going to do this the calculus way. Take the original function, it's a polynomial, and find the intervals when it's increasing and decreasing with calculus techniques. So the original function had a 2/3 x cubed, 2/3 x cubed minus 2x squared minus 126x minus 18. So for increasing and decreasing, if we take the first derivative of a function, that will lead us to finding out intervals when the original graph is increasing or decreasing. So 2/3 times 3, luckily the 3's cancel and you just get 2 for that. Decrease the exponent by 1. 2 times 2 is 4. Decrease the exponent by 1, and the derivative of -126 is just -126. The derivative of 18 is nothing. So once we get a derivative, we want to set it equal to 0 and figure out if it could be undefined anywhere. This is a polynomial, so it's never undefined, but it could equal 0 twice since it's quadratic. And luckily, all these terms divide by 2 also. So x squared minus 2x minus 63. This will now factor x times x. There's a negative in the back, so you're definitely going to get one positive, one negative. You need to multiply to 63. The most common way to do that is 7 times 9. I always start with the most common way. 7 times 9. And then it has to subtract. If there's a negative in the back, you're basically trying to subtract to the middle instead of add to the middle, or you can think of it as adding to a negative. But we're trying to subtract a negative 2. That means the bigger number has to be negative. So 7 and 9, 7 and negative 9. 7 times negative 9 is negative 63. 7 minus 9 is negative 2. So we have two what are called critical numbers, negative 7 and positive 9. So these are your only two chances to have the direction change from increasing to decreasing or vice versa. So in a polynomial, especially when you are moving along the polynomial, it will either increase or decrease until you get to a critical number. There's no way it can change at any other place. And critical numbers come from zeros or undefined values of the derivative as long as they don't make the original undefined. And polynomials are never undefined, so we don't have any issues with that. So put your two critical numbers on a number line and then pick test points in these regions. And you plug them into the derivative function if you want to see if the derivative is positive or negative. So I'm going to plug these into f prime. And it's best to use the original function. We found out earlier that if you use the reduced version, sometimes that can lead you astray. So just to be safe, I'm going to do it in the original function. I'm going to put, well, the easiest one is if you plug 0 in, these x's will disappear and it'll just be negative 126. And we don't really care about the 126 so much, it's just that the derivative is negative. The derivative is negative when you plug 0 in. So that means the original function f is decreasing all the way from negative 7 till 9. And once it's decreasing in one place, it has to be decreasing everywhere in that interval because only at critical numbers can it change. So next I'm going to plug in negative 8 by doing 2 parenthesis negative 8 parenthesis squared minus 4 parenthesis negative 8 parenthesis minus 126. I plugged negative 8 in and got 34 for the answer, but I don't really care about the 34. It's that it's positive 34. So the graph is increasing. The original graph is increasing first, and then it switches to decreasing. For this problem, all we care about is increasing and decreasing portions. But that's actually another concept coming up later. There's if you're increasing first and then you hit a critical number and then you decrease after the critical number, that's also a relative maximum or local maximum, although we don't care about it at this point. But that's what the first derivative test is about, is checking to see if it changes from increasing to decreasing or vice versa. Okay, now instead of plugging negative 8 in, now I'm going to plug in 10 for both of the x parts. Plug in 10, and I also got 34, which that happens a lot where if you go 1 unit this way and 1 unit that way, often the answers are the same in polynomials anyway. So I got a positive there, and it's increasing. So we increase till we get to negative 7. Remember, we don't use these test points in the answer, so you might want to cross them out when you're done. You're going to increase till you get to negative 7. Then you're going to decrease until you get to positive 9. And then you're going to increase forever after. So negative 7 and 9, they would be relative maxes and mins when we get to that later. But for now, we just have increasing from negative infinity till negative 7. And again from 9 to infinity. Those are the two increasing portions. And the one time it's decreasing is when you're between negative 7 and 9. So once you find all this, then the answer looks just like the previous problem when we did it from a graph. Although here they want the critical numbers too. There's a negative 7 and a 9 critical number. It's increasing from negative infinity until -7, comma, and then from 9 to infinity. Whoops, didn't get the 9 to infinity. And it's only decreasing between -7 and 9. Oops. -7 and 9. Okay, so find the critical numbers, increasing, decreasing. Okay, same directions, just a different type of problem. So number 3, original function is x minus 1 e to the -2x. So I got to find the first derivative to see where the critical numbers are. And I've got x minus 1 times e to the -2x. I have two functions of x multiplied together. So this is going to take the product rule first times the derivative of the second. The derivative of e to the -2x is itself at first. And then technically times ln of e, which equals 1. And then times the derivative of the exponent, which would be -2. First derivative of the second plus the second, and the derivative of the first is linear, so it's just a 1 slope in front, so the derivative of the second is 1. So I've got x minus 1 times, I can put this -2 in front, plus, here it is again. You could distribute this to these two parts and get an x, a -2x, -2x e to the -2x, minus, or actually turn into plus 2 e to the -2x. That's a distributive property right there. And then plus this e to the -2x. So all three terms have an e to the -2x. You can pull that out front as a greatest common factor. There would be a -2x left over, plus 2, plus 1. And that parenthesis would be -2x plus 3. So I've got e to the -2x times this, -2x plus 3. And if you set this equal to 0, then you could set each part equal to 0. A product equal to 0 means either part is 0. Well, e to the -2x or e to the x, this is never negative. Exponentials never equal negative or equal 0 unless you shift them up or down. Then potentially they could, but you would need a plus or minus something outside of this to do that. So e to the x looks like this. And then if you put a 2 there, that's a horizontal shrinking, which is similar to a vertical stretching. And then the negative just flips it around this way. It's a reflection over the y-axis because it's a horizontal reflection. And it could be rising a little faster than normal because of the 2. But it never touches the x-axis. That's an asymptote, actually. So this never equals 0, and it's never undefined either. It's got an infinite domain. This is never undefined because it's a polynomial. But this second part does equal 0 one time. If I subtract 3 and divide by -2, positive 3/2. Positive 3/2 is my one and only critical number. So it could have an increasing section followed by a decreasing section, or vice versa, or maybe it's just always increasing or always decreasing. So all I need to do is make a number line with 3/2 on here, plug it into the derivative function, and that'll tell me what's happening to the original function. I would plug in 0 for something less than 3/2 and probably 2 for something more than 3/2. And we need to plug it into the derivative function. You could do either this. You could do this too, because I didn't like reduce anything. I just factored it, which puts it in a different form. So that doesn't really matter which one you do. But if you plug it into, if I plug 0 in right here, this will be e to the 0. E to the 0 is 1. And this will be 0, so you'll just get 2 plus 1, which is 3. So the derivative equals 3 when I plug 0 in. The derivative is positive 3 when I plug 0 in. So the graph is increasing at first. It'll increase from negative infinity all the way till 3/2. So what happens if I plug 2 in? And this might not come out nicely, but at least I can do it in here. So if I do E is second and the negative and the division sign, E raised, and if I plug a 2 in right there, the exponent will be -4. E to the -4. E to the -4 is a positive messy decimal, but it's going to be positive times this. So is this part positive or negative is all I care about. Put a 2 right there, you'll get -4 plus 3, that's -1. So -1 times that, if I multiply this by -1, the derivative equals a negative if I'm anything bigger than 3/2. So first it was positive, then it switched to negative, so there are 2 different ones there. Now it's decreasing. So it's going to increase first until it gets to this critical point, and then it's going to decrease after that. So that would be a relative maximum if they cared about that, but here they just want to know increasing and decreasing. So it increases from negative infinity, negative infinity until you get to 3/2. And then it decreases from 3/2 to infinity. Okay, suppose the function graph below is the derivative function, okay, f prime of x. Find the locations of all relative extrema of f of x and tell whether they're maxes or mins. Okay, so it's different than if you have the original function. If you have the original function, this is a local minimum right here. And this would be a local maximum. And this would be another local minimum. But we're not looking at the original function. So the original function is going to have relative extrema whenever the derivative is 0 undefined. Those are the potential places. A derivative is 0 in a derivative graph anytime you cross the x-axis. If you cross or touch the x-axis, those are spots where the derivative is 0. And then a derivative could be undefined if there was an undefined place of this graph. Now, corner points in original graphs are places where the derivative doesn't exist, but this is not an original graph, so that corner point doesn't necessarily mean anything here. Plus the fact the derivative is below the x-axis before the corner point, and it's still below the x-axis after it. So we're not having the derivative change from positive to negative or vice versa, so it can't be a relative max or min anyway. So we have 1, 2, 3, 4 spots that could be relative maxes or mins. There's 4 critical numbers here. 4 times the derivative equals 0. And in all 4 of them, it's above the x-axis on one side and below the x-axis on the other. So that makes them all relative extrema. If you get a graph like a parabola graph, if your derivative graph looked like this is not the original graph, the derivative graph, then you're above the x-axis until you hit 0, but then you're above the x-axis on the other side. So that means you're increasing, when the derivative's positive, you're increasing in the original function, and then you hit that spot where the derivative is 0, but then you're increasing after it, so that's not a relative max or min when that occurs. It might have been good on this problem if they would have put one of those where you just like move this graph up a little bit so this would just bounce off the x-axis, like in college algebra where you cross or bounce off the x-axis. But all 4 of these are crossing points. So all 4 of these x values are relative max or mins. And if you're positive first and negative second in the derivative, that's exactly what we're doing right here. If you're positive first in the derivative and negative second, that means you're increasing in the regular function first and decreasing second. That's a local maximum. So this x value of negative 9, 10, negative 11 is a relative maximum. And then below the x-axis here, so that's when the derivative is negative. Then I'm above the x-axis here, that's when the derivative is positive. I'm switching from a negative derivative to a positive derivative. That means the original graph is switching from decreasing to increasing. That's a local minimum. Okay. I guess we need to read these boxes a little closer. Okay, so relative maximum, no relative minimum. Okay, though that's not the answer. I need this one, I think. There's a relative maximum at negative 11. There's a relative minimum at negative 8. And then we're going to we're going from positive to negative right here. Positive to negative, that's another relative maximum. There's another relative maximum at negative 4. And then when we get over here, it's negative derivative first, positive derivative second. That's another relative minimum at negative 2. Negative 2. So if you are given the derivative graph, you're always focused in on when are you above the x-axis, when are you below the x-axis. It's a totally different concept to look for when you're given the derivative graph, is what makes this one harder. Okay, so now we're doing like problems 2 and 3, except now they actually do want the extreme as well, but we really do what we did in problems 2 and 3 first when we look for increasing and decreasing portions. So f of x in number 5 is negative x cubed minus 3x squared plus 9x plus 5. So first you take the derivative. Negative 3x squared minus 6x plus 9. And this is never undefined, but it could be equal to 0 twice. It might help to divide everything by negative 3. So that would make positive x squared, positive 2x, and minus 3 equals 0. Now we need 2 numbers that multiply to 3, which is clearly only 3 and 1 if it's going to work. 3 and 1 makes 3 happen when you multiply. There needs to be 1 positive and 1 negative, though, and we're trying to subtract the positive 2 this time. So that means the positive needs to be bigger, positive 3 and negative 1. And then the 2 critical numbers would be negative 3 and positive 1. So put them on a number line, negative 3 and positive 1. I'll definitely pick 0 in the middle. I would pick 2 and negative 4 for the outsides. Plug them into this version, not the reduced version. If you just factor it, then you can plug it into that. But if you actually reduce it, that can actually change some of the answers, apparently. So plug 0 in here and here. You'll just get positive 9. The derivative is positive for anything between negative 3 and 1, and that means the original function is increasing then. If I plug in 2, negative 3 times 2 squared minus 6 times 2 plus 9. If I plug in -2, the answer is -15. So the derivative is negative for any number bigger than 1, and that's when the graph is decreasing. So probably this is going to be -2. Negative also, I mean -3 times -4 squared minus 6 times -4 plus 9 is -15 also. So yep, it's negative first, then positive, then negative in the derivative. So that means the original graph is decreasing first, hits a critical point, critical number, and then it increases after that. So that is a relative minimum. There's a relative minimum by the first derivative test at -3. And again, get rid of your test points when you're done with them. And then it's increasing after -3 until you get to +1, and then it decreases there. So it's 0 for a moment in time at 1. That's a relative maximum. Relative maximum at x equals 1 by the first derivative test. And then if they want the locations of the x values, if they want the values of them too, then we have to plug those extrema into the regular function if they want that. And it looks like they do, yes. So relative maximum is at +1. Relative maximum, the function has both, has a relative maximum at x equals 1, and you'd have to plug 1 into the original function. So negative parenthesis 1 parenthesis raised to the third power minus 3 parenthesis 1 parenthesis squared plus 9 parenthesis 1 parenthesis plus 5. So I just plugged in 1s in these 3 x's right there. And this is the value of it. The value is 10. Has a relative maximum value of 10 at x equals 1. This is what helps us do section 5.4 when we're graphing these things, if we know the locations of them and the values of them. Then there was a minimum at -3, so plug -3 into all these x's. Negative parenthesis -3 parenthesis raised to the third minus 3 parenthesis -3 parenthesis squared plus 9 parenthesis -3 parenthesis plus 5. Plugging in -3, I get a -22 answer. And college algebra knowledge can help here too, because if you have a negative odd degree, the end behavior is up on the left and down on the right, just like this here. So you're starting up high and you come down to the relative minimum first. That occurs at -3, -22 for a coordinate. And then you turn around and go up until you get to 1, 10. And then you just go down forever. And then that way you get the correct end behavior too. So if I just quickly sketch a graph of the situation, make sure these 2 coordinates make sense, and they do. It's not a guarantee I did it right, but if you're supposed to be coming down first and your answer says you have a maximum first, that could be an issue. Okay, on a particular day, the power used in a state could be approximated by this function. T is the number of hours since midnight. Find any relative extrema for power usage as well as when they occur. Okay, so I think this is that one that we had a little trouble with in the homework, because normally it's not till chapter 6 when you look at endpoints for maxes and mins, when it's about absolute max and mins. But because this is a application problem from either business or real life, in this case with a power company, they count the endpoints as possible answers here. Okay, so unfortunately they always give real messy equations when you're doing these application problems. The power involved is -0057 86 t cubed and then plus 1803 t squared minus 0.6975 t and plus 20.58. So the derivative of this will turn out to be quadratic because the exponents are going to decrease by 1. So I need to do 3 times this decimal, 3 times 0.005786, 017358. And it should be negative too. Negative 017358. Decrease the exponent by 1. And then 2 times 0.1803 is 3606. 3606t. And then this part's easy, at least just that constant in front is the derivative part there. And the derivative of this constant is nothing. Okay, so the only way to solve this, unfortunately, is the quadratic formula. And it's definitely never undefined, but it's going to equal 0 twice. So opposite of b, plus and minus square root b squared minus 4 times a oops, I did that backwards, 5/8 times c, which is a negative here, all over 2 times a. So I would do the inside of the radical first. 0.3606 squared minus 4 times negative 0.017358 times negative 0.6975. So the inside of the radical is this decimal. I've got negative 0.3606. Square root of this decimal, 0.8160,354. And the denominator is 2 times negative 0.017358. So the denominator is negative 0.34716. Okay, so let me bring this other answer back up. Okay, so I had the inside of the radical, so I need to take the square root of that decimal. And that is this radical right here has an answer of 28566,333 repeating. So I need to do this negative plus and minus this decimal divided by that decimal. So maybe I can just do it here. Negative 0.3606. I'm going to do the plus first. Plus 0.28566,33333. And then divide by negative 0.034716. So the first answer is 2.158. That's a critical number. And that is between 0 and 24 at least. Let's see if they want things rounded. Round to 2 decimal places at the end. Okay. So I'm going to make that 2.16. One critical number is 2.16. And then the other one is going to come from doing that negative 3.3606 minus the radical number divided by negative 0.034716. The other answer is 18.62. And then it also turns out, because of this application, since we want to go between 0 and 24, then 0 and 24 themselves might be max and mins as well, just because of the application of this. Because this is a negative cubic function, so the graph actually looks like this, like the previous one we just had. And normally it goes forever up and forever down, but they're cutting this off. They're just arbitrarily starting somewhere and ending somewhere 24 hours later. So this may turn out to be, well, this is definitely a maximum, just it's not really supposed to be, but they consider it one here. Because at midnight, the power was whatever it was, and it decreased until the morning when people wake up, and 2 hours later, I guess, then it really reached a minimum at that point. So at 2 a.m., 2.16 a.m., that's truly the relative minimum. And then 18.62 is another one that's a relative maximum. And this is kind of a maximum just because at that moment in time it was going down after that. And then it reached, in fact, this here is lower than what this appears to be potentially. So that is kind of considered a minimum here. But normally you wouldn't consider the endpoints until you're doing absolute maxes and mins in chapter 6. So let's see how they want this answered. First, they want the derivative. So that was right here. The derivative is negative 0.017 358 t squared plus 0.3606 t minus 0.6975. Okay, so there are 2 minimum and 2 maximum. Okay, they're doing these separately. Okay, 2 minimum. 2 minimum. One is the 2.16. That's really a relative minimum. And then the other one happens to be 24 hours into the process just because the power is dropping at that point. So the first is 2.16 hours after midnight. The other one is 24 hours after midnight. And we'd have to plug those into the original function to get their megawatts. Thousands of megawatts. Okay, so I need to plug both of those into the original function. Negative 0.005786 times 2.16 cubed plus 0.1803 times 2.16 squared minus 0.6975 times 0.216 and plus 20.58. So at 2.16 hours after midnight, it's 19.86 for the kilowatts. And then if I redo this with 24s instead of 2.16s, that's 27.71. And then for the 2 maximums, the first one is 0 hours after midnight, right at midnight itself. And the second one is 18.62. The 0 is at least easy because that's going to be 20.58. And then the 18.62, I can plug that in. Maybe if I go back 2 places. 18.6, whoops, 2. 18.6, insert a 2. 18.6, insert a 2. $32.75. Okay, so we'll see if that works this time, because last time I missed the 0 and the 24 that they were considering to be just kind of from practical purposes, that those are kind of high and low spots if you stop at those interval points. Okay, next thing up is we move to section 5.3 where we're doing the second derivative, higher derivatives. So f of x, the original function is 5x cubed minus 2x squared plus 13x plus 3. And they want the second derivative and then plug values into the second derivative. So you just do the derivative twice. The first derivative would be 15x squared minus 4x plus 13. The second derivative is the derivative of the first derivative, so that would be 30x minus 4. 30x minus 4. Plug 0 into that, and you would just get minus 4, because the x part would disappear. Plug in 9. 30 times 9 minus 4. 266. And the fact that the second derivative was negative and then switched to positive, that means somewhere in between it was equal to 0 at some point. And that's in the second derivative, zeros of the second derivative, and potentially undefined places. They can be spots that are called points of inflection. When a second derivative switches from positive to negative or vice versa, that's called a point of inflection. And unlike maxes and mins, they don't have separate names. It's point of inflection either way that it happens. Okay, so now we just want to do higher derivatives, the third and fourth derivative. Okay, we'll have to do the first 2 derivatives to even get that far. The original function is 4x to the fourth plus 2x to the third plus 4x squared plus 4x plus 1. So the first derivative would be 16x to the third plus 6x squared plus 8x plus 4. The second derivative, 48x squared plus 12x plus 8. And now here comes the first answer. They want the third derivative first. 48 times 2 is 96, x to the first plus 12. Since that part's linear. 96x plus 12. And we're not plugging anything into it, we're just listing what it is. The fourth derivative, which they put a little 4 here in parentheses, that since this is linear, the fourth derivative would just be 96. And any derivative after that would be 0, because the derivative of a constant is 0. Okay, so now we're going to use the second derivative test, apparently. So the original function is 4x cubed minus 5x squared plus 1 If I find the first derivative, 12x squared minus 10x. And we're going to need to find the critical values of this. So that's never undefined, but I could set it equal to 0 and find two zeros. In fact, it can divide by 2 and make 6x squared minus 5x. Take out an x GCF, and there would be a 6x minus 5 left over. So x equals 0 is one critical number. And then here you're going to have to add 5 and divide by 6. If you need to do that slower, that's fine, but it's 5 over 6. Two critical numbers. 0 and 5 over 6. Okay, so you got two choices. You could really do this with the first derivative test and nobody would know that you did that. So one option is to do what we did on the other problem, 0 and 5 over 6, and plug these into the first derivative. See if they're positive or negative, and then the original function will be increasing or decreasing based on that. If it switches, when you check this region with this region, if there's a switch there, then you get a max or a min. And then you reuse this region with this one, and again, you hope for a switch to get another max or min. But you really have to look at two calculations at once. And that would not be long or hard to do that, but the point of this problem is if you can quickly take the second derivative, which is pretty easy compared to this first derivative, it would be 24x minus 10. If you can quickly take the second derivative, if you plug critical numbers into the second derivative, even though critical numbers come from the first derivative, it's a little strange. Why would you plug them in the second derivative? But it turns out if you plug critical numbers into the second derivative one at a time, in one calculation, you can tell if there's a max or a min. If I plug 0 into this, I would get negative 10 for an answer. Since the second derivative at a critical number is negative, critical numbers are spots where you are flat in the original graph. But the only way to do that with a negative second derivative is having it concave down. If you're concave down at a critical spot, that has to be a local maximum. So there's definitely a local maximum at x equals 0, and they apparently don't care about the value of it, just the location of it. There's a relative maximum at 0. And if I plug 5 over 6 in, 24 times 5 divided by 6 minus 10 is positive there. So then, if you're positive at a critical point, critical number, you have to be concave up there. That means you're a local minimum. So there's a local minimum at 5/6. There's a relative minimum at 5/6, and there's a relative maximum at 0. And I did that in two calculations instead of 3. So we could have done this, and since 0 turned out to be a maximum, that would mean that it would be decreasing first. No, sorry, increasing first. If we would have done the first derivative test, it would have been increasing first and decreasing second. And then the decreasing would switch back to increasing, and then you would have the minimum at that point. But you could do that if you wanted to, or you could do it to double check things. But I can just tell that this would have to be the answer based on what I got for this answer. So the second derivative test it's the point of it is it's a slightly shorter way to tell relative maxes and mins, if getting the second derivative can be done quickly. Okay, for graphing functions, again, you can go through everything. This is a cubic problem. So we definitely know with a negative cubic, it has to rise on the left and fall on the right. So C and D are definitely out. I could do the first derivative quickly and tell where the critical numbers are might help. And then maybe I could eliminate the other graph that's either A or B, but we don't know yet. Negative 4x to the third minus 6x squared plus 144x minus 12. So the first derivative is negative 12x squared minus 12x plus 144. And this is clearly never undefined, but it could be 0 twice. If I divide by negative 12, that can make things simpler. Whoops, negative 12, negative 12. That would make a 1x squared, a 1x, and a negative 12. So that would factor into x plus 4 and x minus 3 in order to get a positive 1 in the middle. There's two critical numbers, negative 4 and positive 3. And clearly, based on what we've seen with cubic functions, if they're negative, it's going to start up high, it's going to hit a relative minimum first, then it's going to hit a relative maximum second, and then keep going down. So this x equals negative 4 should turn out to be a relative minimum. X equals 3 should be a relative maximum, and I could do the first or second derivative test to confirm that. But since it's just a multiple choice graphing situation, we could possibly tell. Now they don't give me a lot of information here, but if I could see that this was negative 4 and maybe this one's not negative 4, then that could help. Or is this 3 and this is not 3? That's hard to tell here, but so I guess all we can do is, since we know these are the relative mins and maxes, we could find their values by plugging them into the original function. So if I do negative 4 times negative 4 to the third power minus 6 times negative 4 squared plus 144 times negative 4 minus 12, the value of the relative minimum is negative 428. So this low point right there is going down as low as negative 428 on the y-axis. If I plug 3 in instead of negative 4, the relative maximum reaches a high point of 258. So I could use these, now that I knew where those locations were. I needed to use calculus to figure out where those locations were. An algebra student wouldn't have known when this was occurring at its low point. But I can just check, is this more likely to be negative 428, considering this is negative 600? Or is that negative 428? That doesn't seem likely. That doesn't even seem halfway to negative 600 yet. And the maximum was 258. This certainly could be 258, getting more than halfway to 400. This is certainly not 258. That's probably not even 100. So this must be graph A. With a little bit of, well, mostly with algebra knowledge, once I have a multiple choice graphing problem, I could use my algebra knowledge to get most of the answer right. But then I need a little bit of calculus here with the critical numbers to really tell the difference between graph A and B. Okay, same thing here. Some algebra knowledge would help. There's definitely a negative 2 vertical asymptote. The bottom would equal 0 at negative 2. So this cannot be the graph. That's a positive vertical asymptote. This looks like 0 is the asymptote. That's out. This could be negative 2. And that seems to be out. So I already know this is negative 2 just from algebra knowledge. And whenever the degrees are the same in algebra, then the horizontal asymptote is the two leading coefficients divided by each other. So negative 1 divided by 1 is negative 1. This at least appears to possibly have a negative 1 horizontal. It might seem like 0, but notice that this one has a little gap there, and this one, it's hard to tell, but it looks like it does cross over the old x-axis a little bit there. And then we could do our first derivative, second derivative, and that would tell us, if we did the first derivative, it would turn out that the graph's always decreasing. So apparently the first derivative is always negative. And then if we did the second derivative, it would be concave down at first, but then it would switch to concave up after that. So again, if this was not multiple choice, you could do all the calculus side to this, but we can already tell what the answer is without even doing all that. Okay, and then this is the one where they give you kind of clues, like you're a detective and you have clues here and you want to match it up to the graph. We need to be continuous and differentiable everywhere except 2, where there's a vertical asymptote. So this could be a vertical asymptote of 2. This could be, I think that one's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, this one's out because it has the asymptote at 1. The other 3 have it at 2. So we've eliminated C already. The derivative needs to be less than 0 everywhere it's defined. If a derivative is less than 0 everywhere except the asymptote, that means the graph is always decreasing. So it can't be graph A because it's increasing in the first half of it and then it's decreasing after that. Same thing. Well, actually, B is always increasing. So already I know the answer is D because this is the only graph that's always decreasing, other than C that I've already eliminated. Horizontal asymptote at 2, yes, D has that. The second derivative is less than 0 between negative infinity and 2, and 5 and 7, that's when you're concave down. So you're concave down from negative infinity till 2, and from 5 to 7, there's a little bit of a downward bend right there. It's concave up the other 2 times from 2 to 5, and from 7 to infinity it's concave up. So even though I knew the answer was D after clue B, I checked the other 3 just to make sure, and yeah, that is true for all of these are also true on graph D. Okay, find locations of absolute extrema for the function whose graph is shown to the right. So I do not have a closed interval here. This is an infinite interval because of these arrows going up forever. This graph will go up forever, so it's never going to have an absolute maximum. If it was a closed interval, then I would be guaranteed 1 absolute maximum and 1 absolute minimum. But in an open interval or an infinite interval, then you're not guaranteed to get anything. But I can tell this graph goes up forever, so it has no absolute maximum, but it does have an absolute minimum. This C2 right here, there's nothing lower than that. So when does it have an absolute maximum? It never does. When does it have an absolute minimum? At C2. And this is easier to tell when you have a graph given to you, but then we're going to switch to when we don't have graphs next. Okay, so 2 big ideas here in section 6.1. If you have a closed interval, that's done differently than if you don't. So closed interval, I need to find the critical numbers of this function, and then I'm going to use them plus the endpoints of the interval. Those will be the only places to have absolute maxes or mins in a closed interval. So f of x equals, oh, sorry, we're on number 14. X cubed plus 10x squared. This is number 14. Plus 25x plus 1. So first derivative would be 3x squared plus 20x plus 25. And if I set that, it's definitely never undefined, so no critical numbers from that. If I set it equal to 0, we're going to have to factor this, and there's no way to divide by 3 first, so I'm going to get a 3x and a 1x. The best way to get 25 is 5 times 5. Definitely both of the signs are positive too. So does this add up to 20? 5 plus 15, yeah, that is 20. So there's 2 critical numbers. One of them is negative 5. And the other one you subtract 5 and get negative 5 and divide by 3. So negative 5 over 3. If either one or both of these is not in the closed interval, then they don't matter. But I think they both are in the interval. The interval goes from negative 9 to 0. So we have a closed interval from negative 9 to 0. So all we have to do is make a chart. The x values are the endpoints and any critical numbers in between the endpoints. So these 4 are my only chances to get absolute max or mins in a closed interval. And I'm guaranteed to get a max and a min. There may be a tie. There may be more than one x value that produces the max or min, but the value itself only is unique. There's a unique absolute maximum and there's a unique absolute minimum value right now. Plugging 0 in is easy. All these x's disappear. The answer is 1 when you plug 0 in. Let's plug all the rest in. So I need to do, first I'll do -9 parenthesis cubed plus 10 parenthesis -9 squared plus 25 parenthesis -9 parenthesis plus 1. So I plugged in -9 and I got -143. Whoops, I forgot the 1. -143. So I can hit second enter and just type over the -9s with -5s. When we plug -5 in, it's now +1 again. So already there might be a tie for the absolute maximum. And this could be the absolute minimum, but we still have -5/3 that could go either way. But one of these two values is definitely one of the two answers. So now I need to do -5/3. I'm going to insert a divided by 3 on all those -5s. Insert a divided by 3. Oops, I missed it. Insert a divided by 3. Okay, I got to retype this one. -5 divided by 3. Okay, so there's -5/3 plugged in, and I got -17.5. If that was an answer, I probably would not type it in as -17.5 because it's actually a big, long, messy decimal. But it's not one of the answers, so it doesn't matter. So there's definitely an absolute minimum of -143. That's the value of it, and it's a unique value at x equals -9, which turned out to be unique. But the x's don't have to be unique. Then there's an absolute maximum of +1, which is unique, but the locations are not unique. It happened at both -5 and 0. So you get a cubic graph that's positive. They look like this generally. And depending where this interval is given to me, absolute minimum of -9. So apparently at the beginning of the interval is probably like way down here somewhere. The interval's starting down here, and this is the lowest point of the graph in the interval only, but it goes down forever actually. So if I use the entire domain, there would be no absolute minimum or absolute maximum. But if I start at -9, that's the lowest point all the way till 0. And then apparently 0 may be the point where it has a relative maximum too. So, although maybe it's just maybe it's here and here. So maybe this is -5 and this is where 0 is. And they both happen to have a y value of +1 is probably what's happening here. So we don't really care about that, but that's what's kind of going on there. There's an absolute maximum is +1, and it occurs both at -5 and 0. 1 happened at -5 and 0. -143 happened at -9. And never in the interval from -9 to 0 is the graph lower than -143 is what that's saying. Okay, same type of problem. But now we don't have a closed interval, so that's what's different here. We have an infinite interval from 0 to infinity. So this is the other half of this section. One half of the section is when you have a closed interval. The other one's when you have either an open or infinite interval. So the original function is 2x plus 8/x squared. And I'm going to write that as 8x to the -2 to make the derivative easier, plus 2. And our interval is greater than 0 only. Okay, so I'm going to take the first derivative, look for critical numbers. The derivative of 2x is 2. The derivative of this is negative 16x to the negative 3. And the derivative of this is nothing. So this actually could be undefined, because if I rewrite it back this way, then 0 makes this undefined. I would have a 0 in a denominator. But 0 also makes the original undefined, so therefore it's not a critical number. Plus 0 is not in my interval anyway, so even if it was, it wouldn't matter. So I did check for that, but it turned out it didn't matter. So now I'm going to set this equal to 0 and solve it to see what makes it equal 0. You can take this negative fraction and add it to the other side, and then you can multiply both sides by x to the third. Divide by 2. X cubed equals 8. Cube root it. X equals 2. And 2 is in this interval. And here's the key thing for this. If you have any interval at all, but especially when you have an open or infinite interval, if there's only one critical number in that interval, then you have a chance for an absolute max or min. So then what we do is we check, is it a local max or min? If 2 is a local max or min, and I can check that with the first or second derivative test. If 2 is a local max or min, then by default it's also an absolute max or min. And we're only going to get one or the other here. You can never get both with this method. So let's make a number line. I'll just do the first derivative test, because finding the second derivative would be messier and take longer. So I would plug in, you can't plug 0 in because it's not part of the interval, but I would plug in 1 and 3. Plug in 1 and 3 into the derivative. Well, 1's easy because 1 to any power is equal to 1. So 2 minus 16 is negative 14. The derivative is negative when you are less than 2. So the original function is decreasing. The original function is decreasing from 0 to 2. Does it switch to increasing after 2 is the question. So what is 2 minus 16 times 3 raised to the negative third power? Is it positive or negative? It is positive. The derivative is positive after 2. So the graph is increasing. The original graph is increasing after 2. So you're decreasing first until you get to 2. Then you're flat for that moment in time where the derivative is 0. And then you're increasing after that. That's a local minimum or a relative minimum. And if a single critical number in an interval is a local min or local maximum, then it's also an absolute min or absolute maximum. So I just showed that there's an absolute minimum at x equals 2, although there may not be an absolute maximum. I don't know anything about the absolute maximum. Maybe there is, maybe there isn't, but we know for sure there's an absolute minimum at x equals 2, and we could plug 2 into this if we need the value of it. But let's see if they just want the location only. No, they do want the value also. So absolute minimum, there is no absolute maximum. So at x equals 2, and then we just have to plug 2 into the original function. 2 times 2 plus 8 times 2 to the negative 2 power, or you could do 8 divided by 2 squared if you want, plus 2. The value turned out to be 8 exactly. The absolute minimum is 8. So this would never drop below 8 in any of the positive portion of the graph. Okay, so we got 2 sections left. We got 6.4 and 6.5. Here's the start of 6.4 when you're just doing implicit differentiation. And here the variable of interest is x, arbitrarily x. It could have been y, but it's x. In section 6.5, the variable of interest is automatically a third variable, usually t, for time. But I have 2x squared minus 5y squared equals 4, and then they want me to find dy over dx. So this determined that x is the variable of interest. So I'm going to do the power rule on 2x squared, the derivative of that is 4x to the first, and technically there's a dx over dx attached to that, since x is the variable of interest, and this is the variable I was working on. But anything divided by itself is 1. So if the variable of interest is the one you're doing, then you can ignore that part basically, which is why it was always ignored up until this section. But now negative 5y squared, that has a derivative of negative 10y, but now I need to have a dy over dx for that. I'm working on a derivative of y, but x is the variable of interest. And the derivative of 4 is nothing. So here's what I have. Now you just want to solve for dy over dx. You could subtract the 4x over, or I could even add this negative over to the other side. Usually that's what I do, is when one's negative, I would just move the negative over to the other side. That'll make it positive at least. Then you don't have to deal with negatives. Divide by everything but the dy over dx. dy over dx, the derivative of y with respect to x equals 4x over 10y. I could reduce this to 2/5 also. So dy over dx equals 2x over 5y. And typically these answers are going to have both x and y in them. That's the point, is that we have a mixture of variables going on. Whoops. Where before it was always just about x. Now I messed that up twice. Okay, 2x over 5y. 2x over 5y. Okay, find the equation of the tangent line at the given point on the following curve. So my original problem is a circle, x squared plus y squared equals 25. Generally, x is the variable of interest unless they specify otherwise. We want to do this at 3, negative 4. If you have a circle of radius 5, like so, 3, negative 4 would be like right here. So there's a tangent line that's going to touch there once. It clearly has a positive slope, and it's going to come down here and touch the y-axis at a negative value. So the equation of the tangent line is y equals mx plus b always. I can already tell the m is positive and the b is negative just by a sketch of the graph. So do what you did on number 16. The derivative of x squared is 2x, and technically times dx over dx, plus the derivative of y squared is 2y, but times dy over dx. And the derivative of 25 is 0. So do the same thing as the last problem, minus 2x. This time I am going to minus the 2x because the y is already positive. 2y dy over dx, let's forget that part, equals negative 2x. Divide by 2y. And the 2's can even cancel. So 2y's cancel, and we got dy over dx left. The derivative of y with respect to x is negative x over y. If you plug in an x and a y into a derivative, that gives you the slope of a tangent line. Slope of a tangent line is the code word for derivative. And because this derivative has both x and y in it, I really need an x and a y to plug them both in. Put 3 here and put negative 4 down there. You're going to get negative 3 over negative 4, which is really just positive 3/4. The two negatives would cancel. So now we know half the answer. Half the answer is y equals 3/4 x plus some negative value, or minus whatever. So I'm going to write y equals 3/4 x plus b for a second. When you're looking for the y-intercept, then you plug in the x and the y again, just temporarily. Put negative 4 in for y, put 3 in for x, and solve for b. And we already know it should turn out to be negative. 3 times 3/4, you just multiply the 3's and you get 9/4. Subtract 9/4 from each side. So multiply that by 4 over 4. And you would get negative 16 over 4 minus 9 over 4. That's negative 25 over 4. So the final answer is y equals 3/4 x minus 25 over 4. And that makes sense because I could tell the slope was positive and the y-intercept had to be some negative value. 24 divided by 4 is 6, so it's a little less than negative 6. And they already have the y equals here, so I just need 3/4 x minus 25 over 4. Okay, now we're in the final section, 6.5. Now it's all about a third variable, dt. And first they're going to tell you all the variables except for one in the problem. So 18, I have y cubed equals 2x cubed plus 88. And we're told x is 4, y is 6, and dx over dt is 3, but we don't know dy over dt. So the derivative of y cubed is 3y squared, and then you need a dy over dt attached to that because t is the variable of interest. The derivative of 2x cubed is 6x squared, and then you need a dx over dt. This time you do need it because t is the variable of interest. The derivative of 88 is nothing. And then I want to solve for dy over dt. That's the one unknown. They're not going to give me a value for it. So we can divide both sides by 3y squared. Dy over dt. I could reduce this 6 and 3 to 2. I can get a 2x squared over a y squared. And I could just put the dx over dt attached to that multiplied in. And now we can plug in all our values. So x is 4, y is 6. And dx over dt just has a value of 3. And you could plug the values in right here too at this point, before you do the algebra too. So whatever this equals, that's the answer. 2 times 4 squared is 32, divided by 36 times 3. Now it came out weird, so maybe they want it as a decimal. As a fraction. Math, enter, enter. So maybe they want it as 8/3 instead of 2.66666. I got to see if they want a fraction or a decimal. It does say round to 2 decimals, so 2.67. So if x is changing at a rate of 3 units per time, then at the same time y is changing at a rate of about 2.67, a little less than what x is changing by. Okay, here's our cost function. So again, on these problems, this is kind of like the extra assignment you're going to have. When you get your equation, c equals 0.4x squared plus 7,000, 0.4x squared plus 7,000. I need to do a dc over dt for the derivative of c. Then this derivative would be 0.8x to the first, but then there'd be a dx over dt for that. And then the derivative of 7,000 is nothing. So I just do what we did on problem 18 first. And then one of these three things is going to be an unknown, but it could be any of the three actually. So I'm going to read the paragraph and search for 2 other numbers to plug in. Usually it's these 2 that they give you, and usually you're looking for this answer. But we did have one problem in the homework where they gave us this and we were looking for this one. That's always possible, so you got to be careful which things they're giving you. How fast is the cost per month changing? How fast is the cost per month changing? Cost per month. That's this is the unknown here. The cost per month is the unknown. When production is changing at a rate of 11 units per month, production, that's the X. X is changing at a rate of 11 units per month. That's this. This is 11 right here. And then the production level is 80 units, so that's just raw X. Raw X is 80. If I produce 80 units and it's changing at a rate of 11 at that moment in time, then I can figure out how the cost is changing. So 0.8 times 80 times 11, 704. The cost is changing by $704 per unit of time at that moment in time. Nearest dollar, just make sure they don't have like hundreds of dollars or anything like that. Let's see where it says anything about the dollars. Okay, it must just be dollars. So it's increasing at $704 per month. The only thing to watch out for is sometimes in the paragraph they'll say in hundreds of dollars. So then you'd have to add 2 zeros to this, but it doesn't mention anything about that. So you can just assume it's regular dollars. Okay, one last problem, number 20, where we have about temperature going on. And okay, so I'm going to do a similar thing on number 20. I'm going to find the derivative first, and that'll let me know what I need numbers for, and one of the things should be the unknown. So C is the number of crimes. C is crimes. 1/10. T is temperature. And minus 65 squared plus 120. So the derivative of C is dC over dt. It's technically 1, but then you have that part. And then here you can do the chain rule. 2 times 1/10 turns out to be 1/5. Rewrite the base. Decrease the exponent by 1, and then multiply by the derivative of the inside, which is just 1 though. And the derivative of 120 is nothing. And then since t is the variable here, then there needs to be a dt, d capital T over d little t. So just like problem 19, there's 3 unknowns here. There's how the crime is changing, there's how the temperature is changing, and then there's literally a single temperature at a given moment in time. Those are the 3 unknowns. 2 of them should be given to me, and 1 is what I'm looking for. So read the question. The crime rate is rising by blank crimes per month. The one thing we're looking for is how the crime is changing. We're looking for dC over dt. That's the related rate. How is crime changing at a specific moment in time? When the average temperature is 72 degrees, that's the temperature. If the temperature is exactly 72 at that moment in time, how is the crime changing? If the temperature is changing, by the end of May, temperature is rising, positive, rising at a rate of 7 degrees. So this is 7 right here, positive 7. So plug 72 in for T. We don't need these extra 1s. And then plug 7 in for the rate of change of temperature. So 72 minus 65 is 7. I need 7 times 7 and divided by 5. 9.8. So as the temperature starts rising, the crimes start rising too. They're rising by 9.8 crimes per month. Okay, so I've answered all 20 questions now, and let's submit this and see how we did. Okay, got 100% right here, 20 out of 20. All 20 have a green check. So, and it took me just under an hour and a half for that. I gave you 2 hours on this test because it could take longer just because some of these problems take a while, but there's 20 similar questions on the test, and everything on the test is in the homework somewhere. And then you get 2 hours instead of an hour and a half, because I just base it on how long it takes me and then give you some extra time And I could have done it faster if I wasn't explaining and writing it down here too. But so there's all 20. Now we're all good for Unit 3. I am going to still release a video later about that extra assignment for Section 6.5, but I wanted to make sure you had the review since your test is coming up this week, Thursday or Friday. The extra assignment about 6.5 is not due till the end of the semester, so at least you got some time for that.